our speaker today is Zudong Shan, and Zudong Shan is an assistant astronomer at the Institute for Astronomy, University of Hawaii at Manoa. He obtained a PhD degree in physics from Stanford University and a BS degree in Earth and Space Sciences from the University of Science and Technology of China. He is a science working group member for DKIST and science team member of SDO HMI. He is interested in a variety of solar and stellar physical processes, in particular those that involve the magnetic fields. So today his talk is on Today his talk is on the fascinating solar active region 12673. Now I have to share. So can you see?
Yes.
So now to Zudong.
All right, thank you, Masumi, for the invitation and the nice introduction. I apologize for the technical difficulty. So today I'll be talking about this famous active region 12673 that appeared on the sun in 2017. Okay, it's almost 4.5 years ago. So this work, the work I will show are some of our own, including myself and 2 graduate students I'm working with, Jonathan Lee and Jiayi Liu. But also this work has been, benefited with discussion or input from many researchers that are listed here: Slava, Sarah, Brian, Sarah, Masha, Lucia, Pete, and Amy. Next slide, please. So this is the outline. On the left, I'm showing you a HMI video of this active region evolution over about, I believe, 4 to 5 days. So I will give you an overview of this active region. Then I will talk about some of the highlights from the research on this famous LIM XA flare that is a textbook flare. And then I'll talk about our own work on the magnetic field topology and its evolution. The second work I will talk about from my team is about the bald patch formation, including the fast Doppler flow and the inference of energy and elliptic flux. Next slide, please. All right, so here on the left, I'm showing you a timeline of this active region evolution. On the top is the Gauss soft X-ray light curve. And the active region emerged on the sun around September 3rd, actually, 2017. And you can see these 2 large flares on the 6th, that is denoted with 2 red short bars on the top of this top panel. These red bars indicate X-class flares. So there are a total of 4 X-class flares. So 2 on the 6th, on the disk, and then 1 large one on the 10th that is shown on the far right. On the lower left is a mosaic of the evolution. As you can see, this active region started out from a remnant sunspot from an older active region 2 rotations ago. And there's a rapid flux emergence that looks like C-shaped. Okay. And one polarity actually moves westward and collided with the old sunspot and got stopped there. And the magnetogram on the bottom, you can see that it is extremely complex. And lower right is a high pass filtered image of this LIM cavity flux roll system that actually eventually erupted. So this is a most productive cycle of 24. It produced 4 X-class flares and over 20 CMEs. Next slide, please. So one of the, the most significant feature of this active region is that it has one of the fastest flux emergence rates. So on the left is a summary of the flux emergence rate on the y-axis, and on the axis is the actual on-site magnetic flux of one polarity, actually. So these blue dots are actually individual active regions or smaller, ephemeral regions that are that have been characterized in previous study. And these red symbols are from simulation. And the yellow symbol is active region 12673. And you can see the track here indicates the evolution track, right, over several days. And the green symbol shows another famous active region 12192 in 2014, which is the largest active region since 1990. As you can see, it's almost, the peak flux emergence rate is almost as fast as the active region 12192, despite having only about 30% of the sunspot size. And it's much, much higher than most of the other active regions. Now, this plot shows that there's a power law scaling between the flux and the flux emergence rate. And this active region actually lies approximately on this power law shown by the solid curve. The simulation so far seems to have a slightly higher flux emergence rate. Next slide, please. So this active region has really strong magnetic field. Using the infrared observations from Goody Solar telescope, Haiming Wang and his group measured about 5,500 Gauss magnetic field in the photospheric light bridge using just the splitting of the line, the eye. You can just immediately measure the magnetic field strength. And now using the Nobayama radio helioscope, they observe a source in the active region at very high frequency at 34 gigahertz. So if the emission is coming from a gyro resonance, you know that the magnetic field is directly proportional to the frequency that you're observing with. And it is inversely proportional to the harmonic number. That means that the minimal, you can estimate the minimal magnetic field if, and everything above the fourth harmonic number are invisible. So assuming that you're observing a third harmonic, the minimum magnetic field is the frequency divided by 8.4. And you immediately get a 4,000 Gauss magnetic field strength at the coronal base at about 1 megameter based on comparison with extrapolation. Another interesting observation is shown on the left, and that is the post-reconnection loop after the X8 class flare. And what you see here is calcium-2 8542 line observed on the limb. You can see that it's actually, very bright in emission right now. And looking at the Stokes V using just a weak field approximation, you can estimate the magnetic field, line of sight magnetic field. Now, the interesting thing here is that the authors also looked at the dynamics in these loops. So by tracking the dynamics by the brightness variation, you can get a plane of sky velocity. Then if you compare the plane of sky velocity with the Doppler shift observed in the line, you can get a velocity vector of the loop. So you can get an inclination of the loop with respect to the plane of sky. And then you can convert your line of sight magnetic field to the actual magnetic field strength. And if you do that, they found that the magnetic field at the loop top, that is about 30 arcsecond above limb. You can still get a 300 Gauss magnetic field. That is that also sets a record. It's extremely strong. Next slide, please. Now, the X9 flare also gives some nice observations. And this one comes from the SP scan. The SP happened to be scanning the flare ribbons during the X9 flare. And as a result, it records some of the spectra during this white light flare. So this figure is from Lucia Client. She did a clustering of the spectral line using a K-mean method, and on the right, different colors indicate different classes of spectra of Stokes I, actually. Now, on the upper row, I show three characteristic or mean spectra from this clustering. The red Stokes I, as you can see, the absorption line completely went into emission. Excuse me. And you also can see the splitting, the image splitting on top of that. So that's really neat. And this is a white light flare that turns the absorption into emission. Okay. And then slightly further away from the white light kernel are these blue pixels that you see a slight, much shallower absorption compared to the regular ones. And on the yellow color shows you the regular absorption line with a large splitting. Okay. So this is a very nice observation of the white light flare. And you can actually estimate the magnetic field, if you can find a way to model these flare light spectra. People also have observed the naked eye sunquake. Usually the sunquake signal is very weak, so you will need to actually do a lot of processing of the helioseismic signal to actually see it. But this sunquake in this flare is so strong that if you just make a movie of the HMI, for example, HMI Doppler, you can see the waves spreading out. And not only that, the Swedish Solar Telescope took videos in the calcium 84 calcium 2 line. And if you look at the image from the calcium observations, you can actually see sunquakes in the chromosphere as well. That's very neat. And another interesting thing here is that the magnetic field in the photosphere changes very rapidly, and the magnetic topology also changes. And I'll talk about that in a minute. Next slide, please. This activation has a severe space weather impact. It created multiple ET events on the Earth, and it's even detected at Mars. The CME of the September 6 X9 flare created the Geomagnetic Storm. So if you look at the figure on the left, the second to the bottom row is the DST measurements. You see a big dip there on the 8th of the DST index, and that's the Geomagnetic Storm, the rival of the magnetic cloud. The September 10th, the limb flare created a ground level event. That is a large number of picked up by the neutron monitor on the ground. And that is, you can see that actually in the lowest panel of the neutron counts somewhere on the 10th, there's a small peak, okay. And the decay of the valley of the neutron counts on the 8th is actually from the Furbush decrease from the magnetic cloud. So there are about 40 articles on this active region alone in space weather. And so I estimate in total there are probably over 100 articles on this active region. So lots of studies. Next slide, please. Now I'm going to talk about this textbook X8 limb flare. This movie shows the early evolution based on ARA movies, and this is the tricolor one. Hot plasma is actually in blue, and if you look at the pre-flare structure, you can see a clear inverse shear dropped coronal cavity, and that is an indication of the magnetic flux rope erupting. And if you look really carefully, you can see a UV wave actually spreading from the side towards left, and as you can see that. And that is a really global, scale UV wave. You can see these waves getting reflected, refracted in the coronal host, and there are studies on that as well. Next slide, please. Here are a few, different studies. So there are studies on the coronal cavity system as a flux rope. There's quite a few studies on the thin plasma sheet that is trailing the ejecta. Presumably, the unresolved current sheet is embedded in this current sheet. On the left, actually, I'm showing you EUV composite from EUV in yellow, and then the K corona from Mauna Loa Observatory in blue that bridges the gap between AIA and LASCO, and the red shows you LASCO C2. You can see from the first side on the west limb, you see a very thin but very prominent density or brightness enhancement, and that is the plasma sheet. AI captured that. I think ICE was also scanning, both ICE and IRIS was scanning that current sheet at that moment. So get lots of good data there. There's study of the global EUV waves. There is dynamics in the post-reconnection loop top, and there's observation of shock signature in radio and also long duration gamma ray observation from Fermi. Next slide, please. Now, I'd like to maybe go over these really nice observations from microwave imaging from Owens Valley telescope. So this expanded Owens Valley array actually observed the entirety of this X9 flare. So if you have this imaging spectroscopy in a time evolving fashion, so basically for each location, you get a spectra of your microwave. And assuming this particular emission is coming from gyro synchrotron radiation, then you can fit the spectra and infer the local magnetic field. And you can infer the electron spectra from the spectra of the microwave. So if you do that, you can get a map, 2D map of magnetic field in the plane of sky, and also a spectra of the electric field of the electrons. Okay, 2D spectrum. So on the left is the very nice result. The first panel, okay, so is an image of the in AIA, and overlaid are the magnetic field lines from a 2.5D MHD model. All right, so inspired by Lin and Forbes model, which is the analytical model of a 2D flux rope eruption. So now they actually can run a 2.5 MHD model, and by only adjusting a few geometric parameters, they are able to fit the 2.5 MHD model, quote unquote, fit to the observations extremely well, the morphology, right? You can see the current sheet length, the flux rope, and the field lines, okay? They agree with the observation extremely well. And on the left panel, what they show is the current density from the MHD model overlaid on the AIA image. Here you can see these hard X-ray and soft X-ray kernels. The hard X-ray kernel is at the loop top from RESI. We have soft X-ray kernels, and these the loop top source and the soft X-ray source lower down agrees with the standard flare model really well. But what really neat is that if you take a cut along the current sheet, all right, and plot the physical variables as a function of the y-axis, the vertical axis, those are what's being shown in the next three panels. So for the total magnetic field in the second panel, the measurement, okay, from the fitting to the microwave spectra are shown in these black circles. And then by just adjusting a few simple geometric parameters, you can actually fit the Lin and Forbes model, as well as your 2.5 MHD model, the values of the magnetic field, to the observations. And you can see it's extremely well fitted. Okay, that is really amazing, as I see it. And in these models, okay, the X point in the current sheet is marked by this horizontal dotted horizontal line. So that is the X point, because the two sides of the loops are actually converging. So you get a slight increase of the magnetic field. And now if you move downward towards the loop top denoted by Y, there's in principle a null point. Okay, so the magnetic field gets weaker. But since it's a 2.5D, you have a guide field, so the magnetic field does not go exactly to 0, but it's weaker. Now, from the observation, if you assume a typical inflow magnetic field, and if you have a magnetic field, a guide magnetic field, you can estimate the electric field by V cross B. Okay, so that is shown in the as the right symbols in the third panel, and then that also agrees extremely well with the MHD, prediction of the electric field in and out of plane of the sky. And the last one is showing you the portion or the number of high energy particles that is above 300 keV. So that is showing you where the electrons are being accelerated. You can see above the X point, higher up, there's very little high energy electrons. But below the X-ray, you see a really rapid increase of the high energy electrons towards the top of the loop top. All right, and the authors argued that the primary electron acceleration rate is actually right at the Y point, where you have this termination shock, and this termination shock that is acting as the primary electron acceleration. And this spectral observation strongly supports that. I think this is a really, really nice observation that fits the standard flare eruption model. Next slide, please. So that is the previous one was a quite quantitative study along the current sheet. If you look at the global structure, you can also see microwave sources at several other locations. So on the upper right, panel B, the colors shows you the brightness temperature, and then you can see several major sources of microwave, one in the north and one in the south, and presumably those are the legs of the flux rope, right? And the central lower altitude large source is coming from the post-reconnection loops. Okay, that is also consistent with the standard flare model. And then the interesting thing here is that you see this small weaker source higher up at the edge of the flux rope cavity, and the authors argue that those are from the energetic electrons that is being accelerated and shoots upward. Okay, so these observations also, support the flare model in 3D proposed by the Medon group that is shown on in panel D. Now, from microwave imaging, you can also estimate the distribution of the magnetic field in a 2D map. And the Fleischmann et al. Paper in Science looked at the time evolution of the magnetic field. And they found that at the loop top, the magnetic field decreased really rapidly. And the magnetic field actually decreased by about 300 to 400 gauss or over 2 minutes. So that supports that the magnetic energy is being released there. That's also a very nice observation. Next slide, please. Now, this is also a very rare observation that you can see this is HMI actually, continuum, pseudo-continuum off limb. And you can see that the pseudo-continuum can be even observed higher in the corona after 40 minutes. Okay, so that means the loop becomes really, really dense from the presumably chromosphere evaporation. And there are estimates of the density there, which is on the order of 10 to the 12 per cube centimeter. And from forward modeling, the people argued that the emission is probably from hydrogen recombination continuum and free frame continuum, but not so much from the scattering. Okay. As a result, the signal is very weakly polarized. And this might have implications for stellar flare emission, because so far the stellar flare temperature, for example, are estimated assuming that all the white light emissions are coming from the stellar surface. Okay, Now, if you have lots of energy deposition, you might get these huge stellar flare loops that could, in principle, dominate your white flare emission. And that's discussed in the Heinzel 1718 papers. Next slide, please. Now, I'd like to switch gears to talk about some of our own work on the magnetic field. I'm listing a large number of literature here looking at the magnetic field using either SP or HMI magnetic field. People have looked at the interaction of different dipoles. They've looked at the energy and elastic injection. They looked at electric currents. They have carried out nonlinear force-free field extrapolation and data-constrained MHD modeling. They've looked at the cause of eruption, including King instability, Taurus instability, null point reconnection, and so on and so forth. But there's not yet a general consensus. Next slide, please. So what I would like to show here is a special magnetic topology I noticed in this active region prior to the X9 flare, and that is the so-called bald patch magnetic topology. So in 2D, it is illustrated on the lower left corner, where you see the magnetic field lines first originate from the left foot point, then it winds down and forms a U shape that grazes the photosphere, then it winds up. So the location where this U loop touches the photosphere is called bald patch, okay? And mathematically, you can quantify or find these locations along the neutral line by taking the dot product between a horizontal magnetic field and the gradient of BZ. If it's bigger than 0, then that's a bald patch. So a practical way to find bald patch is look at the direction of the horizontal field. If it is pointing from the negative to the positive side, that is a bald patch, all right? In 3D, the things are much more complex. Now, on the lower left is a model from Sarah and Nicole in 2004. So they emerged kinetically a flux rope from the lower boundary. That is the green, flux tube here. And then there are these special sets of field lines that are shown in yellow that tangentially, touches the photosphere. That gives you a S shape, right? And that is the field lines that are threading the bald patch on the photosphere. And that gives you actually a separatrix surface that separates the flux rope magnetic field lines inside, the green ones, from the overlying arcades that are outside, that I'm not showing here. So in 3D, bald patch, when it is associated with shear, usually it indicates the existence of a low-lying magnetic flux rope. Next slide, please. Now here's the observation on the right panel, okay? So this is, you can see an S-shaped neutral line shown in green, and all the yellow circles shows you the location of bald patch pixels, okay? So you can compare that with Sarah and Yihong's simulation. You can also see such a S-shaped neutral line, and the solid yellow curve on the left shows you the location of the bald patch. So in the MHD model, there's only one segment, but in reality, of course, it's more fragmented. But I'd like to draw your attention to the central part that is towards maybe a little bit over half away in the upper side. There's a long segment, okay, of the bald patch that is running continuously for about 10 arcseconds, 10 megameters, excuse me. So this is a very rare case, okay? You have these very strong magnetic field and very extended bald patch, okay? Here, the magnetic field strength is as high as 3 kilogauss in the photosphere. That's extremely rare, because previously, most of the observations are either in emerging active regions with these undulating field lines, or decaying active region with flux cancellation, or below these quiet zone filaments. Right? The field strength is usually very weak, tens of gauss, 100 gauss at most. Here's an exception. It's coherent and it's strong field. Next slide, please. So we performed a nonlinear force-free field extrapolation and figure out a way to accurately, to the accuracy of the model, the location of these bald patch separatrixes. And this is the result. It's a little bit complex. I was going to show you the animation, but interplayable animation, but I don't have the opportunity at this moment. So I just try to explain it, to my best capability. So here on the lower panel, you see the lower panel on the inset. Okay, you see 3 bald patches that are colored in magenta, yellow, and cyan. These are the 3 bald patches that we're paying close attention to. And if you trace magnetic field lines carefully from the photosphere from these 3 segments, you get these winding field lines in yellow, magenta, and cyan. Okay. And on the right, you see 3 different views. Each time I'm showing you the field lines from 2 of the 3 bald patches. You can see these are highly winded, and they are surfaces, and they are intersecting with one another. So the intersection between 2 bald patch separator surfaces, there is a special field line called separator. Okay, the separator would touch the photosphere twice. Okay, because it lies both in the first and the second bald patch separatrices, so it needs to touch the photosphere twice. So we figure out a way to accurately, to machine accuracy, to map these separator field lines, and these are noted by S12 on the upper panel on the right, and S23 and S31. Okay, so these are the magnetic topology, based on the nonlinear force-free field extrapolation. Next slide, please. Now you can also map out the magnetic flux rope. Okay, so this is shown in as the green field lines on the left, looking from the side. And if you make 2 cuts, shown in purple on the left, and those are shown on the right panels. So on the top row is 1 cut, and the color here, the purple color here, shows you the number of twists of these field lines. And the yellow and cyan dots are the cross-section of these separator surfaces with this particular cut. You can see those precisely lie at the discontinuity of this twist. And the same goes with the squashing factor in the middle and the currents. Okay, so the strong currents are sort of restricted within the bald patch separator surface. Next slide, please. If you can click on the movie on the left, or click your mouse once, it should play the movie. Right. So this is a movie of the X9 flare. Okay. So we use the early evolution of the flare ribbons as an evidence to our interpretation of the magnetic topology. Oh, yeah. So the right panel shows the selected field lines traced from the bald patch 1 and bald patch 2, those magenta and yellow field lines. And the green shades are the earliest flare kernels from AIA 1600. You can see the 2 K1 and K2 kernels on the far top. They will be very difficult to interpret if you don't have the magnetic field lines, the bald patch magnetic field lines, because they are connected to the main flaring site only through these bald patch separatrixes. So we would like to argue that the X9 flare initiation probably involves reconnection in the bald patch separatrix surface. Next slide, please. All right. So this is the work from my student Jonathan. So on the left is a movie. Mostly, if you can click on that movie once. So you can see that the yellow symbols, okay, along the neutral line are the numbers of other locations of bald patch. I think this should play continuously in loop. And the post flare, if you compare the post flare and pre flare, you would maybe you can play it one more time for me. So So pre-flare, there's lots of in the yellow ellipse in the center. Okay, lots of bald patch pixels. All right, and after the flare, okay, let's wait a little bit. You can see the disappearance of these bald patch. All right, so these are derived from the high cadence HMI vector magnetograms, 90-second cadence. And so Jonathan used this sequence of magnetic field maps to look at the evolution of bald patch. It appears that in the upper part, in the main neutral line center, the bald patch disintegrated, quote unquote. And in comparison, in lower right, in the orange square rectangle, the bald patch remained similar and survived the X-class flare. Next slide, please. So here are a quantitative comparison of the magnetic field properties. So on the top is a time profile of the median horizontal magnetic field that is parallel to the neutral line, north-south component. All right. So as you can see, after the flare, which is shown by the vertical gray band, the magnetic field enhanced strongly by almost 1,000 Gauss. Okay. In comparison, the lower part is the orange square on the lower right, where the bald patch survived. You can see the magnetic field almost didn't change. All right. So the middle row shows you the magnetic field perpendicular to the neutral line. And in the top part, the magnetic field actually changes sign from positive 200 Gauss to negative 300 Gauss. That means before the flare, if the vectors are pointing from the negative to the positive side, after the flare, it now points the opposite direction. Now it becomes a normal shared arcade, and that is why the bald patch disappeared. All right. Similarly, as comparison, the other location doesn't change much. And if you look at the shear angle with respect to the neutral line, prior to the flare, it's 95 degrees. That indicates that it's bald patch, and after the flare, it's below 90 degrees. It's shared arcade. Next slide, please. Right. So we are trying to interpret this as a consequence of the reconnection in the flare current sheet that proceeds all the way down to the photosphere in the central region. And this is consistent with Ionosphere and Fan's simulation 2007, where they contrast one torus unstable flux rope with a kink unstable flux rope. So in the torus unstable flux rope case, the whole magnetic flux rope entirely erupted. So the reconnection actually proceeds all the way to the photosphere. In that case, the bald patch disappears, similar to this observation. And in the kink unstable case, the flux rope split in two, and the bottom half actually remained in the corona and remained attached at the bald patch. In that case, the bald patch survived. And that means the reconnection in the current sheet does not proceed all the way to the photosphere. So in the case, what we think happened is that in the central region, the flux rope entirely lifts off, and the reconnection proceeds all the way to the photosphere, and that's why we see the disappearance of the flux rope, the bald patch. And the case is different in the southern part because the flare ribbons only, progresses to that part later in the flare. So the reconnection probably already progresses to higher altitude. And the lower, field lines are not affected. So that's our interpretation. Next slide, please. So this is a very nice data constraint MHD simulation from Chaowei Jiang. So what they did was they started from a nonlinear force-free field extrapolation that is metastable, and then the system just goes off. They did not constrain the magnetic field, the horizontal magnetic field in their simulation. But if you look at the lower row, the bottom row, that is the horizontal magnetic field, you see that the field strength still increases, actually, just like what we observed in the simulation. And similarly, in the middle row, the magnetic topology also changes from bald patch to a shared arcade. So that's very neat. Next slide, please. All right, so I just presented the disappearance of the bald patch, but what about formation? Okay, So we think the formation could come from, of the flux rope or bald patch could come from flux cancellation, like shown here by the Van Baalahoyen and Martin's cartoon. So you keep sharing the flux, the shared arcade, and you have applied convergence. The flux would cancel, and you would get these twisted flux rope. So what you need to do critically is to get rid of the small loops after reconnection, which is G and F. The field lines connecting G and F in the lower right panel on the top figure, right? Those need to submerge to get rid of those. So you would expect some kind of downflow there, but that's never been observed. Next slide, please. So I think what is unique about this region is that over about 1 day, you see the top panel is HMI continuum. You see this active region, the two sides actually squeeze towards each other, and it rotates somewhat clockwise and forms this S-shaped neutral line. At the same time, in the middle panel, this is a vertical magnetic field. The orange color shows you the bald patch. In the center, as you squeeze the two sides, you see the bald patch forming. And most interestingly, if you look at the third panel in the lower row, we see a very fast downflow shown as the red color. This is the fast Doppler flow. So in HMI, those fast downflows are in excess of 3 kilometers per second. Next slide, please. Now, if you sample the values along the neutral line and plot it as a function of latitude, to remember the neutral line is mostly north-south oriented, and you stack it over time, that gives you this overview of the stack plots. That gives you the overview of the variables. So in the top, you can see that at about -4 hours, you see this onset of extremely fast flows. And then there's a very sharp transition, at about -8.8 degree, from downflow to upflows, from red to green. Okay, so this downflow is really a very prominent feature. I'm going to skip the rest of this slide. Next slide, please. And actually, let's skip this as well. Next slide, please. Right. So, they also scans this region, and with a higher dynamic range and higher spectral resolution, you get to actually see the super fast downflow in excess of 10 kilometers per second. Okay, supersonic. These have been observed before, and the interpretations vary. So what we think happened is shown by the cartoon on the upper right. Because these magnetic field lines are very sheared, okay, and they are about 35 degrees to the west and about 20 degrees to the south. So we are sort of, observing these flux tubes in an inclined geometry. So most of the flows, even if they are field-aligned flows, they would appear to be projected as a very fast up and down flow. So our interpretation at this moment is that most of the flows are actually parallel to the magnetic field lines. And by the nature that there's a rapid transition from downflow to upflow, there is probably some kind of reconnection going on there. That warrants more study. Next slide, please. So I think I'm going to skip this. Next. All right, I'm going to just show you this plot quickly. So another student of mine, Jiayi Liu, is looking at the estimate of the magnetic energy flux and holistic flux using HMI data. On the left is accumulated energy flux, and on the right is accumulated helicity flux throughout the 3 days. And the 3 different curves are 3 different methods. So the dark red curve is the method from the electric field inversion, PDFI, that Marsha and George Fisher have been working on. Now the yellow curve is another popular method, day for VM, that gives you the velocity. So day for VM does not use the constraint of the Doppler velocity. That is the main difference from day for VM and PDFI. Now if you look at the evolution, okay, over 3 days, because of the contribution of the Doppler velocity, the 2 methods give you a very different estimate of the accumulated energy. Okay. And the same goes with the holistic flux on the right. The data VM and PDFI gives you very different, results. So that becomes a problem, if the most, popular two methods give you an estimate that is several 100% off, there must be something going on. Okay. So what I want to say is that the Doppler velocity could contribute significantly to this energy and holistic flux, and we need to be careful when interpreting the results. And the student is actually looking at the results, what could be causing these discrepancies. All right, next slide, please. Let's keep going. One more slide. Well, actually, I'm going to just stop here. That's what I wanted to say. Okay, so this active region is actually very, very interesting. There are lots of nice literature. Some of them has significant implications, and our work has been focusing on the on-disk observations of magnetic field, and we can learn a lot. Thank you very much.
Thank you, Zudong. Very nice talk. And should we open now for questions? So, any question for Zudong? So in the Mint or Rebecca? Rebecca, please go ahead.
Can you hear me?
Yes.
Yes. Okay, so it's not really a science question, but I wanted to understand, and maybe I missed it. What is the definition for bald patch? What determines what a bald patch is?
Sure. Possibly if you can go back to slide, if you scroll up, let's see. The slide, initial slide of bald patch, let's see, which number is it? 15. Sorry if I went over all these very quickly. Just lots of good studies that I skimmed over.
Yeah, I also dropped for a minute, so it's probably not your fault, it's mine. But I am really keen.
Slide 15, if you can go back to.
Masumi, you're muted. I can see you speaking.
Oh, okay. So I'm trying to go back again. So let's see.
Anyways, what I'm trying to say is that from a 3D point of view, okay, if you think of a regular loop that is rooted as the omega shape, right, in the positive and negative field lines, magnetic flux, right? Yes, it's progressing. For bald patch, it's the opposite. It's a U-shaped field line. Maybe one slide up, 14. Yeah, okay. So Rebecca, can you see it? The top left, yeah. You see the field lines coming up from the positive flux from the left end, then it comes down and it comes back up, right? It's a U shape.
Okay.
In the center. That is the location on the photosphere where the U-shaped loops are touching the photosphere is the bald patch. That is the definition given by, the name is given by Slava.
Yeah, I was wondering, so does that usually imply that you're not seeing the linear polarization signals there because it's under the surface?
Oh,
or just it's called bald patch for no reason,
right?
Historical.
It's actually it's actually the opposite. You don't see any. Well, if it's on the right in the disk center, right? You don't see any circular polarization, but you will see linear polarization because it's,
okay. Yeah.
Yeah. It's by definition, it's on the neutral line, so you don't have a vertical field, but you might have a very strong shear field. Yeah.
No, I knew that. I wonder whether historic is that people didn't measure the linear polarization back in the day and they just thought there was no magnetic signal there. But anyway, thank you for answering my question.
Yeah, definitely. I mean, there were sporadic observations from Bruce, quite a few actually.
Yeah.
Okay, so any other question? Yuta?
Yeah. Hi. Hi, Sudong. Can you hear me?
Yeah.
Oh, yeah. Thank you for a very interesting talk. I have a question about the magnetic field strength of this X9 flare, and maybe in the earlier part you show some results of magnetic field strength and of this flare. And is this the most extreme field value or common for this kind of flare?
Slide 5, Masumi, if you can go to slide 5.
Yeah.
Right. So it's not the most extreme, I would say, because you probably know that there have been reports using SP data even of 6,000 Gauss. So, but this is extreme, right? This is extreme, and this is sort of the first time that you get to observe the magnetic field in the corona because of this flare. Okay, from the this commonly observed chromospheric line, calcium. It's because the flare that creates a large density in these loops that you can actually get the chance to observe the flare magnetic field so high up. And also because of the flare, you get to observe it in radio and microwave. Right? So for the other reported strong field magnetic active regions, I think the only available data are either in the chromosphere or the photosphere mostly. So this is the first time you actually sort of you can get a sense of what it is in a 3D space.
Okay, thank you. Yeah, it's very interesting. And this high density, in my idea, this high density can be related with white light emission in the loop. So this will be very interesting for also application to data flares. Yeah, thank you.
Yuhong?
Can you hear me?
Yes.
Yeah.
Hi. Yes, so very nice talk. I just have a question about the view graph number 8, that the flare, the UV images, the movie. I mean, you see this really striking cavity. Is it because it's right on top? Yeah, you see that dark cavity?
Yeah.
Is it because it's hot, or is it because it's low density, or is it based on the UV, if you do a DEM kind of analysis? Is it because it's depleted, or is it really very hot?
Both, actually. Both.
Okay.
Yeah.
So this would be corresponding to those hot channels people
right.
have. Would you say that?
Right.
It's like a flux forming during the reconnection as a result.
Yeah, I don't know, but probably there are people. Yeah, Ryan is. Yes. Yes, there's Ryan actually looked at this paper. I don't remember in detail whether it's corresponding to a the hot channel, but people have probably already looked at it. Ryan, do you want to comment on that? I think Ryan French was.
Sorry, yeah, my my computer froze just as you called me there. Yeah, I can't remember the details either, but David Long at UCL has a paper from 2018 where they do DEM analysis of the cavity and look at the temperature structure through there. And I'll post a link in the chat.
Thank you.
Thank you. Yeah,
it's a really nice textbook. What's really impresses me actually was the fitting of the MHD to the microwave observations. You can even do that. That's quite amazing.
Any other question? Matthias?
Yeah, I have a question which is maybe a little bit a sideline to what you presented. I was just curious in the very early phase of this active region, when the new emergence happens very close to these existing sunspot, I think you said from an earlier active region. I wonder if this new active region actually pushed the existing sunspot kind of out of, I mean, did the velocity, did the motion of that spot change dramatically during this emergence?
Yeah, that can certainly be evaluated. I think the one of the earliest paper on this one, they proposed, okay, they would just describe this as the emergence, right? The new emergence sort of getting blocked by the old sunspot, if you believe that's rooted deeply. I don't know if they are quantitative analysis of the velocity of the old sunspot. I don't know, but that's certainly doable. If you just look at the horizontal velocity to see if there's any specific changes there. Yeah.
Any other question? Ryan?
Hi, me again. Great talk, by the way. This is probably just a fun hypothetical thought experiment, I guess, more than anything. So this is one of the most observed flares of all time in terms of the range of instruments observing this, and as such, we've learned a lot from this event. If we had, back in September 2017, today's range of instruments, if we had Parker Solar Probe, Solar Orbiter, even DKIST, what more do you think we could have learned about this flare?
Let me know what your DKIST proposal is. You should probably use that. Most of them are pretty valid. Whatever DKIST observed. Okay, first of all, I would think, for the limb one, you can point coordinates there, and look at the polarization, there. You can probably learn a lot. And on disk, okay, if you can do multi wavelength to measure the magnetic field, simultaneously in the photosphere and chromosphere, right? You can, for example, for the bald patch study that I'm interested in, you can tell, one thing you can do is look at the azimuth change, for example, in the Himalayan line, and for example, in some of the, the chromospheric line, right? Like the silicon line, the ones that actually, I don't remember. So if you look at two lines at different heights, you can see the azimuth change, right? Whether it's changing from a bald patch to a normal arcade. So that's what you would expect if your magnetic field is a flux probe and turns back around, right? So in the lowest layer, you see a bald patch. In the higher layer, you would see a normal arcade type. That's something you could look into as well. Yeah, but from DKIST, that's definitely what I would like to see. And one thing that I'm also very interested in is the magnetic field changes during the flare, right? So during that flare, Lucia was showing the SP scan, but that only got one scan. And, you don't get the full time, evolution. So if you can have a 2D spectral polarimetry like you would get from DL-NERSC, you can sit and stare, at the neutral line, and we'll get amazing data, I think.
Nice, yeah. I guess let's hope for some equally as impressive and well-timed flares this upcoming term.
Yes.
Other questions? Okay, I don't see any hand raised. Am I missing anyone? I have a quick question, Zudong, and since I have the slides, I'm taking the advantage of going to that slide where you showed kinetic energy and helicity. Yes, this one. So here, they even though they are showing different results in each of the plots, they are very nicely anti-correlated. The accumulation of energy and accumulation of helicity. Is it physically expected? And could you please explain?
Yeah, I mean, well, we basically estimate the accumulation of the energy and electric flux through the estimate of the surface velocity and electric field, right? So, and then the Poynting flux is just E cross B. Yes, you would, for a large flare to happen, right? You need the accumulation of a large amount of free energy and relative helicity. So you would expect it to go up. But how much it goes up, it's not well known. Okay. The thing I want to point out is that the PDFI and Dayfor VM, when they are being tested on ground truth MHD simulation, red MHD, they perform relatively okay, and the correlation is like 90% something. You won't see such a big difference here. So I think what is really going on is some of the systematic that in the way that we approach the estimation, how we use the data. It could be the data itself is wrong, or it could be that we are interpreting it wrong. And also the problem itself is ill-posed in principle. Maybe we just can't get a very good solution. I don't know. It needs more study, I think.
Thank you. So any other question? Okay, so let's thank our speaker again today.
Thank you so much. Sorry about the technical difficulty.
Yeah, but we resolved it. So it's a very nice talk. Thank you.
Thank you. Bye-bye. Have a good day.
Bye.